50 light years away, there's a rock. Not a gas giant, not a swirling ball of clouds, an actual solid rock, roughly the size of a super-Earth, baking under the light of its star. And for the first time in human history, we didn't just detect it. We didn't just infer it from a shadow or a wobble. We looked directly at its surface, measured the heat pouring off of it, and figured out, molecule by molecule, mineral by mineral, what that world is actually made of. No telescope in history has ever done that before. Not Hubble, not Spitzer, not any observatory built by any nation on Earth. And the announcement didn't come with fanfare or countdown clocks. It came quietly, in a research paper, from a team of scientists who spent years staring at data most people would consider unreadable, until it finally clicked into a sentence that should stop you in your tracks. We see a dark, hot, barren rock. That sentence belongs to a team led by astronomer Laura Kreidberg, describing a planet called LHS 3844b Asimaads. Oh, and it marks one of the strangest, most quietly historic moments in the entire run of the James Webb Space Telescope. Not because it's flashy, not because it looks like a postcard from an alien beach. It doesn't. What it represents is something far more important and far more real. For the first time, scientists directly studied the surface of a world beyond our solar system. The way you'd study a photograph of Mercury, rather than just guessing at what might be down there based on light passing through an atmosphere that may or may not even exist. Let's be honest about something up front, because this story deserves honesty more than it deserves hype. This is not a crisp, colorful photograph like the kind you've seen of Jupiter or Saturn. Nobody pointed Webb at this planet and got back a picture with visible craters and canyons. Or the way you'd photograph the moon through a backyard telescope. Space simply does not work that way. LHS 3844 b sits so far away and appears so impossibly small and faint next to the blinding glow of its host star that no camera, not Webb, not anything currently in existence, could resolve its actual surface into a visual image the way you're picturing. What actually happened is more subtle and, honestly, more impressive. Webb watched the planet pass behind its star, in what astronomers call a secondary eclipse, and in that brief window, it measured the faint infrared heat glowing off the planet's blistering dayside. Using the mid-infrared instrument, or MIRI, the team captured that thermal signature not once, but across 3 separate eclipse events in 2023 and 2024, building up a picture of the planet's composition based purely on how it radiates heat. Here's why that matters more than a pretty picture ever could. Every mineral, every type of rock, every possible surface material radiates and absorbs infrared light in a slightly different way, almost like a fingerprint. By carefully measuring exactly how LHS 3844b's surface glows across different infrared wavelengths, Kreidberg's team could compare that signal against the known thermal fingerprints of real rocks and minerals, the same ones geologists study right here at home. They compared it against basalt, against granite, against the kind of silica-rich crust that makes up much of Earth's continents. And what they found ruled things out just as powerfully as it revealed things. The data showed this is not a world with an Earth-like crust. There's no evidence of the granite-rich, silica-heavy surface that typically forms through plate tectonics and billions of years of water erasing and rebuilding a planet's outer shell. Instead, the surface looks dark, airless, and geologically simple, more like the ancient, unchanged, sun-scorched face of Mercury than anything resembling our own planet. Think about what that actually means for a second. Mercury's surface has barely changed in billions of years because it has no atmosphere to erode it, no plate tectonics to recycle it, no water to reshape it. It just sits there, absorbing the full, unfiltered fury of the sun, one hemisphere permanently locked in blistering heat. LHS 3844 b appears to be living out the exact same fate, just around a different star, 50 light years from where you're sitting right now. Researchers involved in the study called this the next step in genuinely unveiling the true nature of these distant worlds, moving beyond atmospheric guesswork into direct geological interpretation. That's not a small claim. That's astronomers saying, for the first time, we can read the actual rock. Now, here's where the story gets even more interesting, because LHS 3844b isn't an isolated headline. It's part of a much bigger pattern of Webb doing something no telescope has ever managed before. Catching actual light from actual planets, not just the shadows and wobbles astronomers used for decades. Go back to 2022, right after Webb's cameras first came online, and you'll find the telescope's very first direct image of a world beyond our solar system, a gas giant called HIP 65426b. Using a coronagraph, a clever piece of hardware designed to block out the blinding light of a host star the same way you'd cup your hand over your eyes to block the sun. Webb's NIRCam and MIRI instruments captured that planet glowing in infrared light, standing apart from its star for the first time. It wasn't habitable. It wasn't Earth-like. It was a massive gas giant with no solid surface at all. But it proved the technique worked, and it opened the door to everything that's happened since. From there, the pace only accelerated. In 2025, a team led by researcher Anne-Marie Lagrange used that same coronagraph technology, this time built through a partnership between French researchers at CNRS and Durham University in England, to capture something even more delicate, a faint point of infrared light hiding inside the debris disk of a young star called TWA7, roughly 111 light-years from Earth. That faint source, now designated TWA7b, appears to be a planet with roughly the mass of Saturn, but here's the detail that actually matters. It's about 10 times lighter than any planet ever directly imaged before it. 10 times. That's not a minor technical improvement, that's an entirely new category of world becoming visible to us for the first time. The planet sits in a gap within one of the debris disk's 3 dust rings, in almost exactly the position models predicted a planet would need to be to carve out that gap in the first place. Lagrange and her team even ran computer simulations of what a planet shaping that disk should look like, and the simulated images lined up with what Webb actually captured. Co-author Matilda Mellon, an astrophysicist at the Space Telescope Science Institute, put it simply, Webb is opening a new window in terms of both the mass and distance of a planet from its star that was never accessible to observation before, and the pattern kept climbing towards smaller, colder, more Earth-like territory. Later, a team led by graduate student William Balmer at Johns Hopkins University used Webb's NIR cam to directly image one of the coldest exoplanets ever captured on camera, a world called 14 Hercules C, sitting 60 light-years away in a system researchers describe as abnormal, chaotic, and genuinely strange. Most directly imaged exoplanets up to that point had been blisteringly hot, hundreds or even thousands of degrees, simply because heat makes a planet easier to spot against the darkness of space. Cold planets barely glow at all, which makes them almost invisible. Balmer put the significance plainly. The colder an exoplanet is, the harder it becomes to image, so capturing this one represents an entirely new regime of study, made possible only by Webb's extreme sensitivity in the infrared. Researchers studying that same planet noted something bizarre in its atmosphere too. Carbon dioxide and carbon monoxide existing at temperatures where you'd normally expect to find methane instead, a sign of violent, rapid churning dragging gas from the planet's warm depths up into its frozen upper atmosphere. Around the same period, Webb turned its attention to a genuine icon of exoplanet science, the HR 87999 system, a young star 130 light-years away, hosting 4 giant planets that have been a key target for planet formation research for years. Webb didn't just image all 4 planets directly, it detected something in their atmospheres that told scientists exactly how those planets were born. Carbon dioxide. Strong, clear signatures of it in each of the 4 worlds. That detail matters because it points to a specific formation process called core accretion, the same slow, methodical process that built Jupiter and Saturn in our own solar system, where a solid core forms first and then gradually pulls in surrounding gas from the disk around its star. Researcher Remy Sumer, who spent a decade helping fine-tune Webb's coronagraph operations specifically for this kind of work, said the team had been waiting 10 years to confirm the telescope could access planets orbiting this close to their star. And now, finally, the results were in. Let's talk about why direct imaging was considered nearly impossible for most of the history of exoplanet science, because that context makes everything Webb has done feel a lot more staggering. Since the first confirmed exoplanet discovery back in the 1990s, astronomers have found close to 6,000 worlds beyond our solar system, and the overwhelming majority of them were never actually seen. They were inferred. The most common method, called the transit method, works by watching a star's brightness dip slightly as a planet crosses in front of it, blocking a tiny fraction of its light. Another method, radial velocity, measures the subtle gravitational wobble a planet induces in its host star as it orbits. Both techniques are brilliant, and both have been responsible for the vast majority of exoplanet discoveries to date. But neither one actually shows you the planet. You're reading its fingerprints, not looking at its face. Direct imaging is different and dramatically harder because you're trying to isolate a source of light so faint and so close to an object so blindingly bright that the challenge has been compared to trying to photograph a firefly hovering next to a lighthouse from thousands of miles away. For most of the history of exoplanet science, that was simply beyond what any instrument could achieve, except for the rare case of enormous, young, extremely hot gas giants sitting unusually far from their stars. That's exactly why the coronagraph technology built into Webb matters so much. A coronagraph is a deceptively simple idea borrowed from an ancient astronomical event. During a total solar eclipse, the moon blocks the sun's overwhelming glare, and suddenly, structures normally invisible in broad daylight, the sun's delicate outer atmosphere, become clearly visible. A coronagraph does the same thing artificially, using a small physical mask inside the instrument to block the light of a distant star, mimicking that eclipse effect on command without needing to wait for the moon to line up. Yet Webb carries several of these built directly into its NIRCam and MIRI instruments, engineered with a level of precision that took the mission's optical teams the better part of a decade to fully calibrate. Every one of the direct imaging breakthroughs we've talked about, from HIPAA's 65426b in 2022 all the way through the surface study of LHS 3844b, depended on that painstaking engineering working exactly as designed in the cold vacuum of space, a million miles from anyone who could reach up and fix it if something went wrong. It's worth pointing out just how unforgiving that environment actually is. Webb doesn't orbit the Earth the way Hubble does, circling a few hundred miles overhead, where astronauts could once visit it for repairs. Webb sits at the second Lagrange point, roughly a million miles from Earth, held in a stable gravitational balance between our planet and the Sun. There are no repair missions out there, no shuttle flights, no spacewalks, no second chances if a mirror segment misaligns or a coronagraph mask fails to deploy correctly. Every one of these direct imaging results represents not just extraordinary science, but an extraordinary bet that a machine built with millimeter-level precision would keep performing flawlessly, alone, in one of the most hostile environments humans have ever placed a piece of technology. And that's exactly what makes the trajectory here so compelling. This isn't a single lucky snapshot. It's a widening capability, tested and refined mission after mission, target after target, each one pushing into territory that was previously considered completely out of reach. A gas giant standing alone in infrared light. A Saturn-mass world 10 times fainter than anything imaged before it. A frozen planet barely warm enough to register at all. 4 giant worlds whose atmospheric chemistry revealed exactly how they were born. And now, a rocky world whose actual surface composition can be read directly from the heat it radiates into space. Each step forward wasn't inevitable. It required years of instrument calibration, patient observation scheduling, and researchers willing to stare at faint, ambiguous signals for months before they were confident enough to publish. What you're really watching is a telescope teaching itself to see something the human eye was never built for. Actual planets as physical objects glowing faintly against the overwhelming brilliance of their stars. It started in 2022 with a single gas giant standing alone in infrared light. It moved through debris disks and hidden Saturn-mass worlds 10 times fainter than anything imaged before. It pushed into genuinely frozen planets that barely radiate any detectable heat at all, and now, with LHS 3844b, it has crossed into something that changes the entire nature of the search. Not just detecting that a rocky world exists, but reading its surface composition directly, the same way you'd identify a rock sample sitting on a lab bench. Here's the part worth sitting with. Every one of these worlds, HIP 65426b, TWA7b, 14 Hercules C, the 4 giants of HR 8799, and now LHS 3844b, was found using variations of the exact same fundamental idea. Block out the overwhelming light of a star and let the faint glow of the planet speak for itself. That principle sounds simple. In practice, it required building one of the most technologically advanced instruments ever launched into space, precise enough to distinguish a planet's whisper of infrared light from a star that outshines it by a factor of millions. And every successful image, every successful measurement, pushes the boundary further towards smaller planets, cooler planets, planets sitting closer to their stars, the exact kind of world our own Earth would resemble if some distant civilization were pointing a telescope back at us. That's really what this is building toward, even if nobody's said it out loud yet. Researchers behind the TWA7 discovery openly said they hope to eventually image planets with as little as 10% of Jupiter's mass, a threshold that edges dramatically closer to true Earth-sized worlds. Combine that ambition with what LHS 3844b just proved, that Webb can now read a planet's actual surface composition once it locks onto that heat signature, and you start to see the real shape of where this is heading. Not a single dramatic reveal, not one headline that changes everything overnight, but a steady, methodical, almost relentless expansion of what we're capable of seeing, one faint point of infrared light at a time. We are watching, in real time, the earliest chapters of a capability that didn't exist at all just a few years ago. The ability to directly observe other worlds, not infer them, not model them from indirect shadows, but actually see the light coming off their surfaces and read what that light is telling us. LHS 3844. B turned out to be a dark, barren, Mercury-like rock, geologically simple and utterly airless. The next one might not be. And with Webb's instruments only getting sharper through continued calibration, and with newer coronagraph techniques already proving they can catch planets 10 times fainter than anything imaged before, the honest answer to what comes next isn't a guess anymore. It's a matter of when the next faint dot of infrared light resolves into a world and what that world turns out to be made of.